Sounds about right. Never got it. Yeah, like that's what even like. Now I just need to do as much practice as possible before. Yours is perfect. Yeah. Yeah, I'm good. You're spacing on the bed. Well, 4 or 5 weeks ago. Yeah. It's weird because he's only like testing us on the first one. So this whole week, like, I found out I have to have a paper due Sunday, like Saturday. Like, oh, good. Good. Not too bad. Math next week and then Indy and civil on the week after. I don't know. I can do that. I just said we don't talk about this that much. Like, just prioritize.
So I have until 3:20.
Yes.
That's when everybody will bolt.
Yeah, they will get up and leave.
Yes.
When you turn off the lights, if you can remember the spotlight. I think you have to turn it on the spotlight afterwards.
It's my thing.
And this is the Rocks and Stars seminar series,
Yes, yes.
which is why I titled it what I titled. I think, obviously.
When I introduce you, I'll probably ask to stand near me.
Oh,
that,
sure.
So that microphone can pick me up.
Oh.
Okay.
Here. We can stand next to each other and you can hold it.
Okay.
Did you get us?
Yeah. Okay, good afternoon. I'd like to introduce today's speaker. Today's speaker is Dr. Roger Myers from the Aerospace Corporation over in Redmond.
Aerojet.
Oh, sorry, Aerojet. Where did aerospace come from? From Aerojet Corporation over in Redmond. Dr. Myers got his Bachelor of Science in Aerospace Engineering from University of Michigan, a PhD in Mechanical and Aeronautical Engineering from Princeton, and then prior to working at Aerojet, he worked at NASA Glenn. So, Dr. Hunter Myers.
Okay. So I gave a talk here about a year ago, a little over a year ago. Were any of you here? I hope not. No? This is different. It's updated. We've done a lot of work in the last year. But fundamentally, what we're trying to do at Aerojet and actually at NASA, at the various NASA organizations, is to figure out how to get scientists or humans to deep space destinations. And since this is the Rocks and Stars seminar series, of course, the people that we want to get are geologists, right? So that's really what we're trying to do here. And what I'm going to talk to you about is, you know, what are we talking about when we discuss deep space destinations? Where might geologists want to go? Why can't we do it today? Why don't we have a whole bunch of spacecraft going around the solar system today? What's the impediment? What's keeping us from realizing that vision? What are the key cost drivers? That's a hint. A lot of the reason we can't do it today is because it's too expensive. What do we need to take with us? Why is it so expensive? Okay, and that's not just about the stuff that we take, but it's about how we get it there. Okay, it's very important to understand the cost of these missions is not just about what the geologists need to take with them, but it's also about how we do it. So how we might get there, and then what technologies do we not have today that are needed in order to have an affordable, sustainable transportation system that can get geologists to interesting destinations that might be cool places to go. Does anybody in the room want to go interested in deep space exploration? So a few of you. Okay, cool. Anybody interested in, anybody grow up thinking about going to Mars? Okay, so it's good. It's too close. Fair enough. I'd like to be able to have, my job at Aerojet is to try to figure out the way to make that dream a reality. That's what we're trying to do, and it's a lot of it. Yes?
Why go to Mars? Why send geologists there? Why not use remote sensing?
Really, it's that it has to do with the flexibility of humans and their ability to react quickly to unexpected situations. If you think about the rovers that are out there now, and they're wonderful devices, they're incredibly sophisticated devices, but even they struggle with reacting to the unknown. And the whole idea is to try to explore the unknown and be able to respond quickly to the unknown. And so, but it's a good question. I think that's if human space exploration continues to be hugely more expensive than robotic exploration, why do it? I agree. So what I'm trying to do is figure out if it's possible to make it affordable, so that economic argument is not always in favor of robots. Yes?
Your work is focusing on getting them there, transportation?
Yes.
Habitation while they're there.
Correct. I think you have to answer questions about the mass required to sustain the humans in order to answer the questions about transportation. But fundamentally, Aerojet is mainly focused on the propulsion side of that. I work with Johnson Space Center, or other organizations to define the habitats, for example. Okay? But you will see that it's all interrelated. So where might geologists be interested in going? They might want to go to near-Earth objects because they represent really early parts of the solar system. Martian moons, Phobos and Deimos, the lunar surface, and the Martian surface. I'm not a geologist. I don't claim to be an expert as to why these destinations are of interest, but I can refer you to lots of National Research Council reports that explain the detail, the science behind why these destinations might be of interest. Again, our objective is to try to figure out, can this be done affordably so that we can enable that agile exploration, that very responsive exploration by humans, as opposed to the robotic exploration. Just to give you, I mean, Aerojet in Redmond built all of the transportation devices on the Mars Science Laboratory mission that's landing in August. My group actually did that, okay? So if you watch the video of the Mars Science Lab landing, every single rocket you see firing there was built here in Redmond. Okay, so we are an active part of both robotic and human spaceflight. We are doing all of the engines on the Orion spacecraft that's going to replace the space shuttle. We had all of the small engines on the space shuttle. So we are, right here in Redmond, Washington, we have the world's most productive in-space rocket factory. That's a fact. I think it's kind of cool, but then I like rockets, so. Okay, so so the question that we're asking is, if we want to do this, how do we do it affordably? How can we afford to do this? And why can't we do it now? It's money. It's too expensive. The cost per person hour is not something that the American taxpayer wants to pay for. Okay? So the cost of getting anything done consists of two major pieces: fixed costs and variable costs. Okay, and the major question that we have to ask is, for an exploration mission, if I want to go to the surface of Mars, or I want to go to an asteroid or the surface of the moon, how do I get the fixed costs and the variable costs down to a level where we can afford to do it? And again, fixed costs are the costs that don't change with the number of missions. So it's like building the university. The university is what it is. It's not a function of the number of students. It could be half empty or completely full. Okay, so you could have 1 mission a year, or you could have 10 missions a year, and you amortize the cost, right? You spread the costs of that launch pad over all of those missions. Okay, so more missions reduces your fixed cost per mission. The variable cost is the cost of the rocket itself, or all of the hardware, right? And so that's going to be proportional about to the number of launches or deep space missions. And what you have to do is look at all of your architecture to do the mission from a fixed cost and a variable cost perspective. So the key to reducing fixed costs, fly lots of missions. And again, it's fixed cost per mission. And the key to reducing variable costs is simple, high reliable vehicles. Okay, it's one of the reasons, who's heard of SpaceX? Okay, the reason that they're low cost today is because they're very simple vehicles, and we're about to learn a lot more about their reliability as they start to fly more missions. Okay? We hope that we hope everything's great. We'll find out. So there's one other reason. The reason is radiation. Unfortunately, contrary to a lot of the early shows, the science fiction shows on television or a lot of the movies, deep space is not very hospitable. Radiation is a big deal. And given all of our knowledge today, it's looking like, for our current capabilities and knowledge, we need the one-way trip time for humans, for people, to be less than about 6 months. So if I want to go to Mars, I have to get there in about 6 months. Okay? And that's sort of the extreme case, looking out 20 to 30 years. Okay? So the implication of that is, from a transportation system perspective, which again you will see shortly goes right into the cost, you have to have very high thrust propulsion systems for the crew. If you're going to take geologists to Mars or to the moon or wherever, you have to have high thrust propulsion for that crewed portion of the mission. There's really no way around it. So, what are the barriers to getting geologists to deep space destinations? Money, it's too expensive, and trip time. Those two things are the challenge. That's why we can't do it today. So, Aerojet's goal was to figure out, in the context of all of these different destinations, how we could get from Earth to that destination with all of these different phases. You've got to launch, you've got to leave the Earth, you've got to get to your destination, you've got to land, come back. Obviously, we're not talking about one-way trips. If you went to Mars, when you were young and you were dreaming about going to Mars, did you dream about coming back? Probably, right? Not staying forever. So you want this key piece. This is a very important part, is the Earth descent. Because what it means is you have to take your return transportation with you, or it has to be there waiting for you. And so you have to add all of that up when you look at minimizing the total cost. So you got to look at different options in the launch vehicle and different options for in-space propulsion. And again, those translate directly into the cost of getting geologists to interesting destinations while they're still alive, we hope. Okay? So, where are we today? Today, this is the cost of launch, for example. The Falcon 9, the SpaceX vehicle that's going to go up at the end of this month to the space station, costs, depending on how you account for it, $60 to $100 million every launch. And that gets 10 tons to Earth orbit. This is an EELV. It's made by the United Launch Alliance. Gets about twice the payload, costs about twice as much. Another bit of payload, 23 tons, $400 million a launch. Who knows what the space shuttle costs to launch? It was between $500 and $1 billion every time. This is where the money comes in. This is why we're not doing those interesting missions. The Falcon 9 Heavy, I have it in blue because it's a paper launch vehicle. It hasn't flown. There's a plan, hopefully, to fly it next year. It's about twice as much. I don't know what it's going to cost. You look at these curves, maybe it'll be in the $200 to $300 million range. And then the Space Launch System, which NASA is pursuing, is much higher. It's 70 to 130 tons of launch mass. And it's probably going to be similar to the Space Shuttle in launch costs. Okay? Again, very expensive. The point of all of this is that we clearly need the smallest, lowest cost launch vehicles possible. One of the reasons the Space Shuttle was so expensive was it only launched 2 to 4 times a year, sometimes only once. And that fixed cost, which was about $3 billion, you had to put that on one mission. Okay? So if it's only one mission a year, if it's 2 missions a year, you spread the fixed costs over the number of missions. So launch cost is driven by the number of missions, and that is driven by the number of users that you have. If the Department of Defense wants to fly a mission, that adds another launch. You spread the fixed costs over that. If you get commercial launches, now we're suddenly talking about lots of launches, and potentially we can really get the cost down. The difficulty is that the commercial and DoD, they're not interested in these big guys. They're only interested in these guys, the small ones, Falcon 9, Atlas V, and Delta IV Heavy. So if you want lots of launches, you got to figure out a way to get down smaller, maybe the Falcon 9 Heavy. Okay? It's just the reality of what we need to do if we're going to get an affordable way to get geologists to interesting destinations. So now I'm in Earth orbit, and I need to get to my interesting destination, the moon or a near-Earth asteroid or the moons of Mars or the Martian surface. The rocket equation, this is the one equation in this talk, the rocket equation tells you the ratio of how much you start with, how much you end with, the difference being the propellant mass, as a function of the energy change, the delta V, and the specific impulse of the rocket. That's how fast the exhaust is coming out of the back end of the rocket, the performance of the rocket. So specific impulse is performance of your propulsion system. Delta V is the energy change required to do a mission. And the final mass is what you have to take with you. So if I have to have a habitat on the surface of Mars or in Martian orbit, that mass would be your final mass. Let's see, to Mars orbit and back, that would be 12.2 kilometers a second. And then you just plug in the performance of your rocket engine, and that tells you how much you have to launch, M0, the initial mass, in order to get that habitat that you were asking about earlier into Martian orbit. Okay? And that initial mass is what your launch vehicle has to take off the ground. Okay? So that tells you how big or how many launches you need. How big a launcher or how many. So that ties back to money. How much money is it going to cost you to get that habitat to Martian orbit? Okay? So for getting to interesting destinations, these numbers here are bigger than the number of getting from Earth's surface to low Earth orbit. So for human exploration missions, getting those geologists to interesting places, it's really dominated by in-space. So in-space transportation will drive your total cost. And that is actually rocket science, but it's not complicated. It's just that equation, which is Newton's law. It's very simple. But it drives all of the costs. So delivered mass, how much is a habitat likely to weigh? Well, and I'm working with Johnson Space Center and with others, with the Bigelow, who's heard of Bigelow? So Bigelow wants to do hotels in space or habitats in space. And we actually baselined one of their habitats, so one of the inflatable habitats. And it looked like getting 4 geologists for a 1-year round trip, It's a 25-ton habitat, so that's what you got to take with you. 25 tons. Now you think about that number in comparison to the launch capabilities. Okay? How many launches were necessary? The geologists are going to want to do some science, right? They're going to want a rover or two. They're going to want some rock hammers. They're going to want some, who knows what, some good equipment. So we figure 1 to 5 tons of that. If we're going to NEOs or the Martian moon, we don't need a lander. You can just pull up next to them or pull up a few hundred yards away, and the geologists can go out and go do their thing with the interesting rocks. If we're going to land on Mars, though, we need landers. And the landers are very heavy because they have to enter the Martian atmosphere, and then they have to be ready. At least one of them has to carry enough stuff to come back up, or the geologists are going to settle on Mars. They're not going to come home, and that's not going to be a very fun experience for them. So one of these landers, we always figure 3 are necessary. 1 includes the surface habitat. 1 is the one that's going to bring them back up. And 1 includes all of that other stuff that they need. They're going to need an oxygen factory, et cetera. So we're talking about 25 to 50 tons of cargo, but not all of that has to go fast. Remember, the humans have to go fast because of, who remembers? Radiation. Yes. But this stuff can go slow. It can take years, a couple years, right? So most of this can be delivered robotically. All of this stuff can be landed robotically if you're going to Mars. Or it can be pre-positioned at a NEO. The key is to separate the time-critical stuff, the stuff that has to go fast, the people, and the stuff that doesn't have to go fast, right? You don't pay FedEx to take everything for next day delivery, right? Some of it goes UPS, some of it goes shipping, etc. So, what are some options for propulsion? And again, if you look at the rocket equation, you will see that for most of the propulsion system, this exponent is going to be pretty negative, which means that the multiplier, the initial mass is going to be many times the final mass. So if I have to launch 25 to 50 tons, if I have to deliver 25 to 50 tons, I'm actually going to have to launch several hundred tons. A lot of mass, and that's money. So if we can somehow use high specific impulse propulsion, like electric propulsion, to do the cargo and use chemical high thrust propulsion or nuclear thermal rockets for the crew, for the high thrust, that kind of a transportation architecture will get us the lowest possible cost because it drives the launch vehicles to be smaller. Okay, so these are the 3 realistic options for the next probably 30 years. I can't see, and this is my field, I can't see a credible way of having other options here, right, for these kinds of big missions. So keys to reducing cost: separate the crew and the cargo. You want to think about your transportation architecture to optimize the transportation system for the application. Like I said, you don't pay FedEx to take stuff that you don't need next day, right? You want fast, high thrust for the crew because of radiation, and you want slow, high specific impulse for the cargo, right? Just like we have on Earth, we have lots of different transportation systems, lots of different kinds of trucks and cars and boats and, you know, all that. We have to adopt a transportation system philosophy. So it's a real different paradigm than what NASA, for example, typically has used in the past. You also, as I said before, you want to maximize the number of missions or launches in order to spread the fixed costs over a large number of launches. Okay? To do that, You want to maximize commonality across missions and markets. And what I mean by that is that you want the same rocket to be used for commercial, NASA, DoD missions, to maximize the number of launches, spread those fixed costs across a large number of missions, right? So you want to, that will give you a large number of launches. And it also reduces variable costs, because if you can get your production rates up, then you can increase the efficiency of your production line. But the biggest impact is spreading the fixed costs. You also want to use a modular approach, because what you don't want to do is have to develop very mission-specific vehicles or transportation systems. You want vehicles that you use, once here, and then you just build another one of the same thing or two of the same thing and strap them together and use that. So when you so you really have to avoid unique one-of-a-kind vehicles. It's very important if you're trying to, if it turns out that getting geologists to deep space destinations is a cool thing to do, we're going to have to do this to make it affordable. So for example, you might launch cargo, use a solar electric vehicle to transfer the cargo to your destination. This is geology on a NEO. This is the example. Then you launch the crew here. There are two launches in this particular example. There are lots of different, these are called concept of operations charts. And essentially what you have to do is go through the details of the mission architecture to make sure you get all of the chunks, everything you need to your destination and then home. So then the high thrust system takes the crew, they do their exploration and come back on a high thrust vehicle. By doing that, we really reduce the amount of launch necessary. This is geology on Mars. Again, we use solar electric to carry the cargo, pre-position it, so it's there and checked out by the time the crew even launches. This one actually uses nuclear thermal rockets for the crew. As I'll say later, you don't really have to do that for many of the missions, but for sustainable, if you want to send geologists to Mars frequently, or like once every 2 years, you end up having to develop the nuclear thermal rockets, okay? Which is quite doable. They were actually tested a lot in the 1960s, for those of you who are familiar with the NERVA program. Aerojet actually developed them. So give you some examples here about some numbers. This is the total mission initial mass in low Earth orbit. So that's what you have to launch, the mass you have to launch. And this is to get 4 geologists to low Mars orbit. And these are for different scenarios, different transportation architectures. So for example, if I have a liquid oxygen, liquid hydrogen crew vehicle, and I use that same vehicle to take cargo, I have to launch 519 metric tons off the surface of the Earth. Okay, that's a minimum of 4 of the biggest launchers that I showed you, just to do this. Okay, to get 4 geologists to low Mars orbit, I'd have to do 4 of those missions. It actually turns out to be 5 when you look at the details. On the other hand, if I just do the cargo with Hall thrusters, the electric, one kind of electric rockets, and I use the same kind of cryogenic LOX hydrogen transportation system for the crew, I drop that almost by a factor of 2. So I have to pay for half the launch costs if I do that. And I can even get it down with the nuclear thermal rocket for the crew and the solar electric for the cargo. I can get it down below 200 tons. So 2 of the SLS launches. Or if I parse it differently, I can do several of the Delta IV launches or the Falcon 9 Heavy launches. Okay? Now this is for a direct return mission. The difference here, I didn't talk about it, but they're different. They're just different ways of re-entering the Earth's atmosphere. Direct return is if they don't go into Earth orbit on the return, and a LEO return is they come into Earth orbit, and then something like one of the commercial crew vehicles They might go to the ISS, the International Space Station, for example. And it's more expensive to do LEO return because you have to take the propellant to go into Earth orbit. And that's actually turns out to be a very high, a large amount of propellant. Okay? But again, the point, you can always drop by more than a factor of 2 the total launch mass by thinking about a transportation architecture. Okay? So again, separating cargo and crew, using solar electric for cargo and high thrust chemical or nuclear thermal for crew decreases the launcher requirements by about a factor of 2. By the way, the same thing is true for any robotic mission. The Mars Science Lab could have been launched on a much smaller launch vehicle and been a lot less expensive if they had used solar electric to get it there. But they elected not to. So when you've got to put all of this together, we've got how do we get what are the crew vehicles? We've got the Orion vehicle, which is being developed now by NASA. There are various commercial crew options, the Dream Chaser, the SpaceX Dragon, the Boeing CST-100. Those are all options to getting to low Earth orbit. And then you need to have a space habitat. So ultimately, all of these things have to be built, and they have to fit within your budget if we're going to take the geologists to deep space. Okay? We need the solar electric tug. In fact, we need 2 of them, 2 different sizes. We need the LOX hydrogen stages. There's obviously some good science equipment that the geologists will need. The nuclear thermal stage, again, is necessary only if you're going to do this multiple times, if you want a sustainable exploration program. Okay? And then you need landers. So what we did was we took all of this data and the orbital mechanics of all of our missions, and we asked ourselves, how much would this cost to build all of these things and do all of the missions that are necessary to get the geologists all the way out through Mars. We actually planned a sequence of missions. The first one was to lunar orbit, and that's really because we need more experience with humans and how they deal with deep space radiation. And then after that, we went to a near-Earth object, an asteroid. Then after that, we went to Phobos and Deimos. And then after that, we had a mission to the Martian surface. So you take all of that stuff and you get the total costs. But there is some development you need to do beforehand. Before when you try to build those costs, you need to know what we need to spend money on now. And the key is, you got to have, right now electric propulsion systems are in the tens of kilowatt range. We've actually tested 100 kilowatt electric propulsion, but it's not ready for flight. The power system is also not ready. The typical the space station has a couple hundred kilowatts of power in terms of the solar array. Okay, and that's the biggest one that's up there now. The efficiency of those solar arrays, anybody have a clue as to what typical solar array efficiencies are today? Actually, it's about 30. State-of-the-art solar arrays are about 30% efficient, something like right in there. It's about 28 to 32, depending on how you add it up. The ISS solar arrays are 12%. Why? Because they were built in 1980, in the mid-80s. Okay, that's when they were built. So there needs to be some development there. Long-term cryo storage. If you send astronauts out with either nuclear thermal or a LOX hydrogen chemical rocket, like the space shuttle used, they have to go into Mars orbit, for example. And in order to do that, you got to be able to have the fuel to fire the rockets, so that you need at least to be able to store cryogens, liquid hydrogen, for 6 months. That's sort of the minimum. In truth, you need to be able to do it for more than a year, because they then have to come back. So We also need in situ propellant production. If we're going to go to Mars' surface, you can actually delay the timing of that because of the overall mission architecture. But you have to be able to, at a minimum, extract liquid oxygen or oxygen from the Martian atmosphere. There are ways of doing that. There's water on Mars. I like to say that Aerojet discovered water on Mars. Why? Because when the Phoenix lander landed, who knows Phoenix lander? Anybody? Okay, a few of you have seen those pictures. Well, you've seen the pictures of the rocket nozzle with the cleared dust and the white patch of ice underneath it. What was the rocket nozzle that cleared the dust, right? So that means that my rockets that I built blew the dust away and melted some of the ice, and there are little water droplets on the landing strut, if you look in detail at the pictures. So I like to claim that we discovered water on Mars. The JPL guys would have a problem with that. But they're all my friends, so. Anyway, so we could further reduce the cost of this if it was possible to go to Phobos and Deimos and do the same propellant production there for the landers, okay, and for the Earth return. So you could definitely reduce the cost more if this was possible, but we don't know enough about those bodies to be able to say whether that's possible. So the nuclear thermal, again, it's necessary for sustainable exploration, and what I mean by that is that the Mars synodic period, the orbital mechanics of Mars say that we can essentially do a mission about every 2 years, but the delta V every 2 years varies. It changes, and in fact, it changes by a lot. Okay, and so in optimal years, when the delta V is lowest, we can do it just chemically and solar electric. Okay, so we can do this with chemical rockets and solar electric. But if it's not optimal, we need NTR or we need a lot more ISRU, in situ resource. And again, all of this, the whole point of all of this is that the in-space architecture dictates what you have to launch. The money is in the launch. Okay? The question is, how do you get that down? And a lot of people don't recognize that for deep space missions, the size of the launcher is dictated by your transportation system on the in-space side. What do we want to do, for example? For example, this is a little bit more detail on the solar electric. We ended up choosing a 150 kilowatt module with a Hall thruster. And again, you would use this vehicle, which would have 3 of these modules in a 300 kilowatt vehicle and 5 and 4 in a 600 kilowatt vehicle. But the bottom line is that you'd use it to pre-position all of this non-time critical hardware. So there's the habitat that we talked about, the consumables, all of your oxygen, food, all that stuff would be there before you left. The Earth return stages, the landers and ascent vehicles, and the ISRU plant. And by separating out these things and using this approach, you drive down the launch costs. You have to have various different stages for the human transportation, the crewed vehicles, and these are just 3 different vehicles that we found were necessary. This is all LOX hydrogen in this particular case. Why LOX hydrogen? Anybody know? The performance is high. It's 450 seconds. It's the highest performing credible chemical propulsion system. Okay, so that's why LOX hydrogen. In situ manufacturing of propellant, there are a couple of options here. One is just making liquid oxygen. We found that you needed to make about 40,000 pounds of the stuff on the surface of Mars. You could also, we actually baselined also making methane, and then you'd burn the liquid oxygen and the methane to do your ascent. For crew consumables, we said you'd definitely make all of your oxygen for breathing, and we also assumed about 10,000 kilograms of water, since we know there's water on Mars, right? So again, the mass savings in IM LEO is huge by doing this. So ISRU enables about 200-ton reduction, which is an SLS launch, which is probably about $1 billion. So by doing this, we've saved $1 billion. Okay. Nuclear thermal, this is actually a plot of the delta V, and you can see it varies a lot. We didn't go up to the maximum. The maximum is off the chart here. But it varies a lot, even within the minima. So you can see the minima here varies up and down, right? And that's because of the eccentricity of the Martian orbit. So NTP turns out to be required for a sustainable crew exploration transportation system. And it's really because we don't want to just do one mission here and you know, one mission about once every 15 years. That would be kind of boring, right? We'd like to be able to go more frequently than that. And to do that, you need nuclear thermal. So again, I talked about the 300 and 600 kilowatt cargo tugs, and we've gone through preliminary design. My friends at NASA Glenn have done 100 kilowatt testing. Again, I worked there for 8 years before coming out here. And we at Aerojet have done up to 20 kilowatts for flight application. So again, every one of these is sized to take a certain kind of cargo and pre-position it. That's the idea. So you take all of that information and you ask, how much is this going to cost? And for these, you know, if we use only a 70-ton launcher, so that's the first, that's like a Falcon 9 Heavy or the first generation of the Space Launch System. We use only cryogen, liquid oxygen, liquid hydrogen crew transportation to the NEOs and Mars orbit. We use liquid oxygen methane for the lander and the ascent vehicle at Mars. We use solar electric for all cargo. So it's all robotically pre-positioned. And we did include, because we want to do stuff after 2034, we did include the development of nuclear thermal rockets, but we didn't have to use them even for the first Mars surface campaign. So what we did first was, there's a whole bunch of non-recurring engineering. That's what NRE is. It's one of those fixed costs that you need to spread, okay? So you got to do a whole bunch of engineering, provide jobs to a lot of UW engineering graduates, right? Then we want to go to the NEO and Phobos, and because of the orbital mechanics, those missions overlap a little bit. So we have one set of astronauts, or geologists, sorry, going to a NEO, and another set of geologists going to Phobos. And that's in the 2022 timeframe, 2023 timeframe. And then we can do a Mars surface campaign in the 2030 timeframe. Okay? The president just was talking about going to Mars orbit in this timeframe. What we're talking about, what we're saying is that if you do it right, you can actually make it a Mars surface mission and have happy geologists on the surface of Mars picking up cool stuff, right? So all of this is called a SAND chart. So essentially it's the dollars per year. So this is annual expenditure in millions of dollars versus year. So if we started this year, by 2031 we could be on the Mars surface for these kinds of dollars, okay? Which is within, the cool thing is that this is within NASA's current exploration budget. It looks like a lot of money to us, but the reality is NASA's budget is about $17 billion a year, and the human spaceflight budget is about $4 to $5 billion a year. So we found that if you do it right, you can fit within the NASA budget, okay, for this kind of mission, which is different than what most other people are saying, because they're actually trying to do it all chemically. That's the big difference. So again, we first go to lunar orbit to gain experience with radiation. We want the geologists to have the experience of being six months in lunar orbit or at one of the Lagrange points. And we need the medical data from that mission. So do that in about 2018. Go to a NEO in 2024. go to Phobos in 2025, and Mars surface, and they'd actually get there in 2033. They launch in 2031. So again, a combination of technology development in the areas that I mentioned, right, and commonality, so that you have lots of mission and spread the fixed costs, are the keys to doing this within our current budget projections. Because I think that the probability of getting significant budget increases is 0 in the current economic climate. Okay? So, keys: separate cargo and crew. Don't try to do it all with one transportation system. It increases your flexibility, it increases the robustness of your transportation system, and it allows you to increase commonality in the overall architecture and spread the fixed costs across a large number of missions. Okay? So commonality is the key to all of this. And it's both in the launch and the in space. Okay? Use the same stuff to go to the moon as to go to near-Earth asteroid or to go to Phobos and Mars. Use more of them, but the same stuff. Pre-positioning non-time sensitive cargo with high performance SEP, solar electric propulsion, drops the cost by a factor of 2. Okay? If you want sustainment, you need nuclear thermal, because the people have to go fast. Right? If the people have to go fast, you have 2 choices in the next 30 years, right? And so if you want sustainable, we're going to need nuclear thermal. And then the last one is, as we learn more about Phobos, Deimos, and the surface of Mars, we may be able to significantly expand the use of in situ resources and even further reduce IM LEO. So again, what we set out to do was to figure out how could we affordably send humans to explore, right? That's what we want to do. Several of you raised your hands and said that was kind of cool, right? That might be interesting. And the reason we haven't done it so far is money and radiation. That's fundamentally really the reason. Okay? And so what we set out to do was to find a way to do it. And we did, I think. So last year, I was on a National Research Council committee looking at technology investments at NASA. And we successfully got them to agree that the top 2 priority investments that NASA needs to make are electric and nuclear thermal. Radiation is up there in the top 10 too, so radiation management. Okay. So that's the talk. Any other questions? Yes?
Why can't we get the radiation medical data from the ISS?
Why can't we?
Get the medical data about the radiation?
Because the ISS's orbit is within the Earth's magnetosphere. Okay, and so that really changes the radiation environment, as you know, right? High-speed charged particles are deflected by the Earth's magnetosphere. Anything else? Yes? Well, the 25 tons that we had a blanket of water. It turns out water is a really good radiation shield. And you need water to drink, right? So what we did was we used a Bigelow habitat and we filled the wall with water. So that's how we mitigated it, okay? And thicker, more water, or, you know, there are lots of concepts for very big magnetic fields or things like that, but the power requirements for that, the mass requirements for that drive your launch costs also. So I wish there were a magic bullet, a magic radiation protection suit. We haven't found it yet. But good question, yes?
What was the capacity for the Saturn V?
130 tons. So it's just what we're about to get back to.
Yeah, what we're trying.
Correct. We agree. I have no problem with you shaking your head that way. Anybody else? One of the problems with the Saturn V, though, is if you look at the fixed cost to operate that, and you and you do one mission a year with a Saturn V, it's really expensive. It was significantly more expensive than the space shuttle. Okay, which is one of the reasons that the SLS is a little scary from a cost perspective, right? Fair enough. We are doing the SLS, and what we're trying to do is to say the SLS, I think, is necessary for crew mission, for the crew piece of the missions. And I think that you can use smaller launchers for the cargo portion of the mission, right? And that gets your cost down as low as you can get. In fact, that's the baseline architecture that I talked to. Okay?
Well, thank you very much.
Okay. My pleasure.